Hey guys, welcome back. We're going to continue today with our integration strategies. We're going to do the more advanced integration techniques. These would be BC only topics for any AB students that uh, have been watching this series. And we're going to look at integration by parts, integration by partial fractions, and then improper integration in this episode. So let's begin with integration by parts. And I'm going to really highlight two key ways of doing integration by parts. So if we begin with an example, integration by parts is very easy to recognize. U sub is not a possibility, and I look at this problem, it almost looks U sub ready, but the x squared and the 2x would need to trade places for this to be a U sub problem. So instead, we have to deal with it via integration by parts. We could do this the long way, but anytime we have a power of x multiplied by e or sine or cosine, we're going to do the table method to do this quickly. So we're going to define our u and our dv. U is something that we can take the derivative of easily, and it goes to 0. So x squared, we're going to derive it all the way down to 0. E to the 2x, we can anti-derive over and over again to match. So we're going to anti-derive as many times as we need to match the table. So 1/2 e to the 2x, 1/4 e to the 2x, and then lastly is 1/8 e to the 2x. And then we just multiply. We're going to go diagonally. We're going to keep the sign the same. We're going to go diagonally. We're going to negate, diagonally multiply, and keep the sign the same. So our antiderivative will be x squared times here. So x squared over 2 e to the 2x minus 2x times a fourth. So that's going to be x over 2 e to the 2x plus 2 times an eighth. So it's 1/4 e to the 2x and then plus c. So it's a lengthy antiderivative, and we're about to go over the original way to do integration by parts in the next problem. It would take a while for this one. So I would know how to do the long way. I'd be comfortable with the formula for doing this the long way, but also know the shortcut so you can get through a problem like this pretty easily. Okay, let's go ahead and look at our next one here. All right, this time let's make it a definite integral just to switch things up. And for the most part, when U sub is not a possibility and you see natural log in the problem, integration by parts is a good bet. And this one we're going to do the long way. So with the long way, we're going to define our u and dv. U is something that you take the derivative of easily and it gets simpler. Dv is something that you can easily anti-derive. And in this case, it's easy to want to put x here because that's normally what goes, but if we think about it, ln x does not have a simple antiderivative, so it can't go in the dv side. So we're going to put ln x on the u side and then put x dx on the dv side. Then we will take the derivative of u, which is 1 over x dx, and then we're going to anti-derive dv to get v, which is going to be x squared over 2. Our formula for integration by parts that you need to know is uv minus the integral of v times du. It's our voodoo formula for this method. It's one you just want to know. It's one that they have a tendency to ask about for problems that even involve a real answer, but something involving generic functions f of x or g of x or something like that, like we've seen in our review work. All right, applying this formula, u times v is going to be x squared over 2 times ln x minus the integral of v times du. When I multiply x squared over 2 times 1 over x, I can reduce the x's down and just get x over 2 and then dx. Then we're going to anti-derive, so x squared over 2 ln x. This will become x squared over 4. And then instead of a plus c, we're going to evaluate this problem from 1 to 2. Notice the way that I work with this. I get the whole thing done. I take the entire antiderivative, and then at the end of that, I evaluate over the interval, making sure I plug 2 and 1 into both parts. So starting with 2, if I plug in 2 here, that's going to be 4 over 2. So 2 ln 2, and then minus 4 over 4, so that's minus 1. Minus, when I plug in 1 here, ln of 1 is 0, so that goes away, and then minus 4. All right, and let's finish it off. We have 2 ln 2 minus 1 plus 1/4. So 2 ln 2 minus 3/4. That's it. All right, so lots of different problems with integration by parts, anti-driving inverse sine, anti-driving inverse tan, problems involving ln, e's, sines, cosines, all that good stuff. And also just knowing this formula for generic functions that you might have to work with for your response or multiple choice. Great, let's look next at integration by partial fractions. And we went over a lot of different variations of partial fractions in class this year. And I would know all of those. So this would be a topic I would say, let's go back and look a lot more than I can fit into one quick video. But let's look at an example of what it looks like and how you solve it. So here's a problem that we're going to use integration by partial fractions for. There's no u sub possibility. The denominator is factorable. So that's how we're going to begin. Factor the bottom, I can rewrite this expression as 8 over, this would be x plus 3 times x minus 1. So to set this up, our goal is to decompose this fraction and break it apart into two fractions that are a constant over x plus 3 plus another constant over x minus 1. Then we're going to solve for a and b. We're going to cross multiply a times x minus 1 plus b times x plus 3 would have to add up to make the numerator, which is 8. Then we're going to pick x values to help us solve. So I'm going to start with x equals 1. When I plug in 1 for x, a goes away, and I get 4b is equal to 8. So b is 2. And then when I plug in x equals minus 3, b goes away, and I get negative 4a equals 8. So a is equal to negative 2. Now, when I rewrite this, I'm going to write it as integrals. I'm going to slide the coefficients to the front. It's really useful when you have fraction coefficients, which happens a lot on these problems. And now we're going to anti-derive. And these are easy ln's. This is negative 2 ln absolute value x plus 3 plus 2 ln absolute value of x minus 1. And then comes my favorite part, is condensing these down. So I can rewrite this as division, right? Since it's subtracted, I can move these powers also up. So I can raise the x minus 1 to the second and the x plus 3 to the second. The one that's negated is going to go to the denominator. So here's my ultimate answer. And I probably at that point, I could have dropped my absolute values because it's squared. There's my condensed version of this. Just having a little bit of fun. Okay, lots of variations of that one. Not going to do them all here. Go back and review them so you're ready to go. All right, last thing today is improper integration. What do you do when a definite integral either has a limit of integration or within the interval of an infinite discontinuity, or if the integral itself goes to infinity, like if you're finding the area of an infinitely large region or volume of a solid that extends forever. So let's look at first the case where you're approaching a vertical asymptote. So if we imagine the problem 1 over x from 0 to 1, this problem has an infinite discontinuity. It's got a vertical asymptote at x equals 0. So anytime this is the case, your first job is to rewrite the problem as a limit statement. Now, I rewrote this one as the limit as a approaches 0 from the right, because I'm working on the right side of 0, from 0 to 1. That's to the right of 0 on the graph, and then a to 1. Now we anti-derive. So this will be the natural log from a to 1. So the ln of 1 minus the ln of a. ln of 1 is 0, so we get negative ln a. Now, as a approaches 0, ln is still undefined, so this is a divergent integral. That area from 0 to 1 under the graph of 1 over x is not defined. Okay, let's look at another example. Let's go to one that deals with an infinite limit of integration. So we're going to take the integral from 1 over pi, I know, bear with me, it's weird, to infinity, and then 1 over x squared times the sine of 1 over x dx. Okay, just like the last one. Anytime you deal with an infinite limit of integration, your first step is going to be to rewrite this as a limit. Like that. Now we have to figure out the way to anti-derive, and based on our previous work, the last lesson, you should see the use of here. You see the derivative connected. The derivative of 1 over x is a multiple of 1 over x squared. So 1 over x, take the derivative, is negative 1 over x squared dx. And then I don't want the negative, so I'm going to move it over. Now, in the previous episode, I did my definite u sub integration by changing my limits of integration in terms of u and then evaluating. Let's do it differently this time. Let's switch it up and try it the other way. Let's first rewrite this as an indefinite integral, so negative. And then the 1 over x squared and the dx are replaced by the du. And the 1 over x is replaced with u. So we would get this in my rewrite. The antiderivative of sine is negative cosine. Because of the negative on the outside, it's going to go back to a positive. So we're going to get the cosine of 1 over x. And then we're going to evaluate this from 1 over pi a. Okay. So now let's put this in. We're going to get the cosine of 1 over a minus the cosine. And when I plug in 1 over pi into 1 over x, we're just going to get pi. So what happens now is a goes to infinity. This 1 over a approaches 0. So this cosine would approach 1, cosine of 0. Minus cosine of pi is negative 1, so plus 1. So this one does converge. It converges to a value of 2. So the area under this graph from the value of 1 over pi to forever would approach a value of 2. Okay, that's it for today, guys. If you have any more questions about any of these strategies or want to go a little bit more in depth with one of them, please let me know. And I look forward to seeing you guys next time.